Lectures 11 and 12 are about the method of partial fractions, and this we can apply to rational functions. And in order to integrate rational functions, we create something called a partial fractions decomposition for it, which is much easier to integrate. Before you study this method, you might want to review some of your pre-calculus. Remember, a polynomial is just a linear sum of powers of x, and its degree is the highest power of x appearing in its expression. So, for example, x to the 5 minus x is a polynomial of degree 5. And the basic result is the fundamental theorem of algebra, and this is the one we use to get our partial fractions decomposition. And this tells us how to decompose these polynomials into their most basic parts. And so it says every polynomial can be factored into factors that are of the form, they're either linear, of the form ax plus b, or quadratics, polynomials of degree 2, which are irreducible. And that just means that they have complex roots. You can identify them by checking the value of b squared minus 4ac. If that's less than 0, then this is an irreducible quadratic factor. If it's greater than or equal to 0, you can further reduce this quadratic into a product of linear factors. And you see here the factorization of x to the 5 minus x. It's x times x minus 1 times x plus 1 times x squared plus 1. And x squared plus 1 is an irreducible quadratic because it has no real roots. There's no real number for which x squared is minus 1. And so this polynomial x to the 5 minus x has 3 linear factors and 1 irreducible quadratic factor. And now our main interest is in rational functions, which are quotients of polynomials. And if a rational function is a proper rational function, that is, the degree of the numerator is less than the degree of the denominator, then it has a partial fractions decomposition. I can write it as a sum of partial fractions, which look like this, depending, of course, on the factorization of q of x into its linear and irreducible quadratic parts. And I can write this function r of x over q of x as a sum of functions that look like this, either a over a linear factor to some power, or ax plus b over a quadratic factor to some power. And if you think about it, we can integrate anything that looks like this using the techniques that we have from before. And here are 3 examples. These might appear in the partial fractions decomposition of a rational function. And you could integrate this first one using the substitution u equals x plus 1, and then it becomes a logarithm. And the second one you could break up into 2 parts, 2x over x squared plus 1 over x squared plus 1. And this, of course, you use tan inverse, and this one again. And for this third one, you might complete the square here, and then use a trig substitution. So the moral of the story is that for any proper rational function, we can break it up into a partial fractions decomposition, and we can integrate these partial fractions using techniques that we've studied before. The simplest case is when the denominator of our rational function q of x can be written as a product of linear factors which are all distinct. And in this case, to create the partial fractions decomposition of r of x over q of x, we include one term for every factor of q of x, and we write r of x over q of x equals some constant over the first factor plus another constant over the second factor plus etc., plus a constant over the last factor. And of course we know everything in this equation except for these n constants, a1 as far as an, and we can solve for those. There are a number of ways. We can multiply this equation by q of x, and this gives us an equation in polynomials, and then we can compare the coefficients, which gives us a system of linear equations to solve. Or we can be clever and plug in particular values of x to eliminate terms and narrow down our search. Let's look at a simple example. If I want to integrate 1 over x squared minus 25, here the r of x is 1, the q of x is x squared minus 25, and q of x has distinct linear factors. It's x minus 5 times x plus 5. And in the partial fractions decomposition, we're going to include one term for each of those linear factors. So here we have 1 over x squared minus 25 is equal to 1 over x minus 5 times x plus 5. And when I'm setting up the partial fractions decomposition, I include one term for each of these two factors. So I set it up as a over x minus 5 plus b over x plus 5. And now I have an equation. 1 over x squared minus 25 is equal to a over x minus 5 plus b over x plus 5. And my next goal is to solve for the a and the b. So here's my equation again. And I can multiply both sides by x squared minus 25, which factors to x minus 5 times x plus 5 to get this equation here, and you can see there will be a lot of cancellation. So on the left, everything cancels. I'm left with 1. In this particular term, the x minus 5's cancel, and I'm left with a times x plus 5 in the first term. And then in the second term, the x plus 5's cancel, and I'm left with b times x minus 5. How do I solve for a and b? Well, one method is to be clever, maybe eliminate this term here by letting x equal 5, and that gives me 1 equals a times 10, and a equals 1 over 10. And then I might eliminate this term by letting x equals minus 5, and I get b equals minus 1 over 10. Another method, the one I mentioned previously, is to take this equation, which is really an equation identifying two polynomials, and if you have one polynomial equals another, then the coefficients of the powers of x must match on both sides. So I tidy up this right-hand side to find the coefficients of the powers of x, and I can rewrite the equation as 1 equals a plus bx plus 5 times a minus b. And now comparing the coefficients on both sides, I must have a plus b is the coefficient of x on the left, which is 0, and 5 times a minus b is the constant on the left, which is 1. Now I have two equations in two unknowns, and I'm quite sure you've seen a method of solving those. I end up with my solution is a equals 1 over 10 and b equals minus 1 over 10. And at the end of the day, what I've done is I've changed this rational function into its partial fractions decomposition. I now know that 1 over x squared minus 25 is 1 over 10 over x minus 5 minus 1 over 10 over x plus 5. Now both of those terms on the right I can integrate using logarithms. So my problem is essentially solved. The next most complicated situation is when q of x the denominator of my rational function breaks up into linear factors, but I have at least one repeated linear factor. In other words, if I write the factors in the form aix plus bi to the k, I have at least one of those powers k is greater than 1. And in that case, I proceed as before, except when I have a factor which appears k times, on the right-hand side, I include k terms in the partial fractions decomposition for it. And the k terms look like this. They're a1 over the linear factor itself, plus some other constant over its square, plus, etc., plus an nth constant, or a kth constant, ak, over that factor to the power of k, which is the power with which it appears in the factorization of q of x. Let's look at an example. If I were to expand this rational function, which is a proper rational function, the highest power above is x cubed, the highest power below is x cubed times x squared, which is x to the 5. So it's a proper rational function. According to my claims, it has a partial fractions decomposition. What does that partial fractions decomposition look like? Well, you see q of x is already factored here, so that's good. And I have repeating factors, repeating linear factors. So I have an x minus 2 to the 3 and an x minus 1 squared. And what this is saying is that for each of those repeated factors, I include terms that look like this on the right-hand side, except that an there should be an ak. Well, so for the factor x minus 2 cubed, on the right-hand side, for the partial fractions decomposition, I include a term a1 over x minus 2 plus a2 over x minus 2 squared plus a3 over x minus 2 to the cubed, and I stop when I get to the actual power of that factor that appears in the factorization of qx. And then for the x minus 1 squared, I include two terms, b1 over x minus 1 plus b2 over x minus 1 squared. Then I equate these two, and I can proceed as before to solve for the unknown constants here, a1, a2, and a3, and b1, b2, and then all of these terms I can integrate using logarithms or the power rule. And we will do this example in class. You can see it proceeds as before, and we'll look at the solution in class. The next most complicated situation is when I have quadratic factors, and in this case I am assuming I have distinct quadratic factors here. So assuming I have no repeats among my quadratic factors, and I may have also linear factors in q of x, for every quadratic term, for every quadratic factor, I include a term in the partial fractions decomposition that looks like this. aix plus bi, where the ai and the bi are unknown, over my known quadratic factor, which appears only once in the factors of q of x. And note that we can integrate all of these either using our tan inverse, our substitution, or trigonometric substitution. So for example, suppose this is my rational function that I want to integrate, x squared plus x plus 1 over x cubed plus x. It's a proper rational function. it must have a partial fractions decomposition. It's a product of linear factors, which I know how to deal with, and one single quadratic factor which doesn't repeat. So the claim is for every quadratic factor I include a term that looks like this in the partial fractions decomposition. So the first step is to find the partial fractions decomposition of that. So I include one term for the single linear factor, a over x, and then for the factor x squared plus 1, I include a bx plus c over x squared plus 1. And now I proceed as before. I multiply across by qx, and I cancel wherever I can. I compare coefficients. On both sides, I end up with c equals 1, a equals 1, b equals 0, and I find that my partial fractions decomposition for this particular rational function is 1 over x plus 1 over x squared plus 1, which is of course something I can integrate very easily. Whenever I have repeated irreducible quadratic factors in Q of x, I include a term that looks like this, an expansion of the factor in the partial fractions decomposition. So if I have something that repeats k times an irreducible quadratic, I include a term a1x plus b1 over the factor itself, plus a2x plus b2 over its square, plus, and I keep going until I get to its highest power appearing in the decomposition, and then I include something of the form akx plus bk over the highest power. And that, of course, should be a bk and an ak, because I'm ending after k steps. And note, to integrate things like this, we might be able to use regular substitution, or we might have to use trig substitution. So as a final example, suppose I want to integrate this rational function. It is a proper rational function. Highest power in the denominator is going to be x to the 5. The highest power in the numerator is x to the 4. And conveniently, q is already factored for us. So for every one of these, we do have a repeated quadratic, irreducible quadratic factor here in the denominator, and I must include multiple terms in the partial fractions decomposition for that particular factor. So the partial fractions decomposition of this rational function is going to look like a over x for that single linear factor, plus bx plus c over x squared plus 1, plus another term, dx plus e over x squared plus 1 squared, because that irreducible factor appears twice. And then, of course, I continue to integrate. I solve for the a, b, c, d, and e using the technique that I showed you before. We multiply across by q of x, then we cancel wherever we can. You might use particular values of x, or you might compare coefficients as I have done there, and you end up with a equals 1, c equals 0, b equals 0, d equals minus 1, and e equals 0. So at the end of the day, the partial fractions decomposition of this rational function is 1 over x minus x over x squared plus 1 squared. And then we can integrate these using a variety of techniques. If a rational function is not a proper rational function, in other words, the degree of p is bigger than the degree of q, then I must use my division of polynomials to rewrite this in this form before I attempt the partial fractions decomposition. So I rewrite this improper rational function some polynomial plus a proper rational function, a remainder over a q of x, the denominator, where the degree of the remainder is less than that of q of x. And here's an example. I would have to use long division to rewrite this rational function as a polynomial plus a proper rational function. And I would get x cubed minus 25x plus 1 is x times x squared minus 25 plus 1 using long division. And then dividing by q of x on both sides, I see that the rational function is just x plus 1 over x squared minus 25. And we've already solved the integral of 1 over x squared minus 25 earlier. And the final topic in this section is rationalizing substitutions. So sometimes we can make a substitution which allows us to convert an integral to a rational function. So in this case, the trick is to let u equal the square root of x, and then du is 1 over 2 times the square root of x dx. And we see when we make this substitution, we end up with the integral of 2u squared over u squared plus 1 du, and we can use polynomial division to rewrite that as 2 minus 2 over u squared plus 1, and now we don't need any partial fractions decomposition to integrate that. That's relatively easy. We already know how to integrate it, and then we convert back to x's and we're done.